My next speaker is Sai, who's one of the experts in using Citus. Like probably no one has converted more applications to using Citus than Sai. So he has a lot of knowledge around how best to distribute your data and best to take advantage of a distributed Postgres cluster. So without further ado, Sai, take it away.
Hi, folks. So today I'm here to talk about efficiently distributing Postgres with Citus, how to choose the right shard key, also called distribution column. So before I get started, I quickly want to introduce myself. As Marco already did, I'm Sai Srirampur and you can call me Sai. I'm the customer engineering lead for Citus at Microsoft. And in my day-to-day, I help customers implement Citus and Postgres, including coming up with right data models, right sharding strategies, migrations, and so on. I was an early engineer at Citus Data. I've been working with Postgres and Citus since past like 6-7 years. And trust me, I love them a lot. A quick fun fact about myself is I love playing ping pong. And one question I've not yet been able to answer is whether I love Postgres more or ping pong more. So let's get started into the talk. So before I get to the crux of the talk, I wanted to cover some like important concepts on, what is Citus, how Citus distributes tables in a Postgres cluster, what is a distribution column, why is distribution column critical, and all of that. So what is Citus? Citus transforms Postgres into a horizontally scalable database. Citus is implemented as an extension, not a fork. Hence, it supports, the latest Postgres versions, and it also supports newer Postgres versions on the day of their release. Citus is a fully open source database, and there is also a fully managed database offering in the cloud on Azure called Hyperscale Citus. Citus gives you the power to distribute tables across multiple machines in a cluster and transparently query them the same way you query with plain Postgres. In the Citus architecture, as you're seeing on the screen, there are multiple nodes. The coordinator node stores metadata and is responsible for distributed planning, whereas the workers store the actual data, and that is where the actual computation happens. Both coordinator and workers are plain PostgreSQL databases with the Citus extension loaded. To distribute a table, you can create tables as you typically do with Postgres. For example, here I'm creating the campaigns table. Then to distribute the campaigns table, you run a simple command called create distributed table, as you're seeing on the screen. Once you run this command, Citus transparently creates shards across worker nodes, the blue dots that you're seeing on the workers. Shards are nothing but simple plain Postgres tables that hold a set of your data. Here they would hold a set of companies as I'm distributing the table on the company ID. By the superpower of distributing tables in a Postgres cluster, you get multiple benefits. Like first is for your application, you get great performance. As you're sharding data, you have like, shards which are smaller tables. There are smaller indexes by which in general you get better index hit rates, cache hit rates for queries. And you also get the power to parallelize your queries in a clustered environment with Citus. The second benefit is you also get scalability. So Citus gives you this ability to add more nodes and rebalance your distributed tables in an online way to the new nodes. This is exactly for the case where your application is growing, your performance and scalability requirements are growing, and you want to keep up in a very worry-free way. So Citus lets you do that. So the magic function that does all of this, right, like that provides you the ability to distribute a table is this function called create distributed table. If you see the second argument, you have the distribution column, right? Choosing an optimal distribution column for an application workload is a prerequisite for efficiently leveraging Citus. Let us do a quick deep dive into what is a distribution column and why is it important. So a column that distributes data across nodes in the form of shards in a Postgres cluster is the distribution column. Citus uses hash distribution under the covers to distribute data across nodes, and it uses the Postgres native functions that it provides for different data types. Distribution column decides how queries are executed on Citus. If you're querying for a single distribution column value, Citus routes the query to a single node, executes it on the right shards, and then gives you the results. Whereas if you query across values, Citus basically does a map reduce. It parallelizes the query across multiple machines and gives you the results. Distribution column can be of any native data type. There are no restrictions there. But more commonly in the real world, you see like, integers and string-based columns as distributed columns. Here is an example of what happens when you query for a single, distribution column. Here I'm querying for the company ID on the campaigns table. Citus routes the query to the right worker node where the company exists and gives you the results. Whereas if I run the query across multiple nodes, I mean, where I'm querying across companies. So here I'm doing an average, doing a group by across like multiple companies. Citus parallelizes the query across multiple shards. It does a map reduce. So here, if you see, the average is translated as a sum and count across the shards, and then the coordinator node would do the division, right? So the Citus extension has all the logic to plan queries in a distributed environment. And this logic not only extends to simple lookups, it also extends to joins, aggregations, window functions, CTEs, etc., etc. So you might be thinking why distribution column or a shard key is critical for applications that are built on Citus. So shard key dictates what kind of performance and scalability that your application gets with Citus. For example, a key that causes queue across nodes is not optimal for performance. Suppose I have a distribution column whose one of the values is 50%, then this value would go and reside on a single node, and that node can become the bottleneck while your queries are getting executed. Key with lower cardinality can affect scalability. Suppose I choose a distribution column whose cardinality is 2, then I'm bottlenecked on the number of nodes I can scale. So I can scale to only 2 nodes. So you want to pick a distribution column with higher cardinality, at least in the hundreds, thousands and tens of thousands. Joining two large tables with different shard keys can be slow because this would incur data shuffles across the cluster. Hence, you want to choose a common shard key across large tables. I'll do a deeper dive into this particular concept in my next slide. But at a high level, you want to choose a common distribution column for your large tables. A column that incurs query parallelism across nodes might not be optimal for all workloads, right? Say for transactional workloads where your query latency requirements are in the single-digit milliseconds, query parallelism can be an overkill, and it could actually add overhead to your queries because there is extra network hops, there is connection handling that Citus needs to do to execute them in parallel. Rather, for transactional workloads, you want to route the queries to the right worker node, optimize the network overhead, still scale memory. Because remember that finally all the data is split across multiple nodes. Whereas query parallelism will be suitable for analytical workloads where you want a single query to use all the compute horsepower in the cluster and maximize the performance. Another concept that is closely related to a distribution column is something called as collocation. This is very important. Tables sharded on the same distribution column values are collocated. So same distribution column values for both tables are on the same worker. Once I distribute two tables on the same column. So in this example, if you see, I have two tables that are distributed on the site ID column, right? Citus ensures that a single site ID for both the tables is on the same worker node. So here, if you see, site ID 1 is on worker 1 and site ID 2 is on worker 2 for both the tables. So collocation helps optimize joins across tables. If I join these two tables on site ID, then Citus can join locally on the worker nodes without shuffling data, because it can basically push the join down across the collocated shards where the same distribution column values exist. So assuming that we have learned why choosing distribution column is important, there are 3 steps involved in building scalable apps with Citus. First is classifying your application workloads to the use case where Citus shines. It can be either multi-tenant SaaS or real-time operational analytics or high throughput transactional workloads. Second, once you've classified the workload, based on that, identify the most optimal distribution column and classify your tables as distributed or reference. I did not touch the topic on reference. So reference tables are tables that are, just replicated or copied across multiple nodes. and smaller tables are good candidates for this, or tables that don't have the distribution column are like good candidates for reference tables. Third, once you have identified the distribution column and you did the table classification, keep some simple considerations in mind while building the data model. And in this talk, I'll focus on the first two steps, the workload classification and identifying the right distribution column. Third step is out of scope for now, as I just have like 25 minutes, and I can take like, any questions on that like offline. So let us iterate through each of the workload to understand how can you classify your applications and choose the right distribution column. So the first set of application is a multi-tenant SaaS app. So most B2B SaaS apps are multi-tenant. Some classic examples of multi-tenant apps are like a Salesforce or a Shopify. Each tenant can only interact with its own data. So whenever I think of multi-tenant apps, an apartment complex analogy comes to my mind, where there are multiple families who are tenants, and each family deals with its own apartment, right? Like, so I wouldn't go and tweak Wi-Fi router settings or thermostat settings for another family, another tenant, right? So each tenant can only interact with its own data. Typically, these apps have like hundreds to thousands of tenants and are growing. Primarily, these apps are like operational and transactional in nature, and from a database query standpoint, latency requirements are like in that single-digit milliseconds. So they are very like sensitive to latency. These apps can be newer apps that are expecting tremendous scale in the near future, or existing apps that are outgrowing a single node database. Typically, the data model in these applications is very relational, and they are built using ORMs like Ruby on Rails, Django, Hibernate, etc., etc. And based on my experience, I've seen these tables as they are these like use cases as they are relational. The number of tables is on the hundreds side, if that makes sense. Once you have identified that your application falls under this bucket of multi-tenant SaaS apps, picking shard key is pretty straightforward. Here I have an example of Shopify's data model. With Shopify, you can easily create like e-commerce online stores, and each store interacts with its own data. A store cannot see transactions of the other store. In this data model, I have a bunch of tables, as you're seeing on the screen: stores, products, orders, line items, and countries. If you observe, stores is at the top of the hierarchy. Products, orders, and line items are for stores, but they are lower in the hierarchy. So they're basically, related to stores. Whereas the countries is not related to stores. It's a smaller table, and it is shared across like, stores. In such an example, the store ID, which is at the top of the hierarchy and which is the natural dimension or the identifier for the tenant in the application, is the right distribution column. In the data model that is ready for distribution with Citus, as you're seeing on the screen, all tenant-specific tables have the tenant ID and are distributed. Rest of the tables that are shared across tenants or are smaller are reference tables. In the Shopify data model that we went through, right, like you have stores, product, orders, and they already have the store ID, right? But for the line items, I was able to add the store ID because of its relationship with like, products and orders. Now, once I have the store ID present on the tables, I can easily distribute them across, multiple nodes in the Citus cluster. So for migrating existing multi-tenant apps, add and backfill tenant ID on larger tables that are tenant specific. The smaller tables can become like, referenced. For newer apps, build them the right way. Like make sure to have the tenant ID present on all the tenant specific tables. Now, why does it make sense to distribute multi-tenant SaaS apps on, tenant ID? The main advantage is you can co-locate all the data across all the tables for a single tenant on a single node. So there are multiple benefits because of this. One is it helps provide SQL coverage. So like foreign keys, joins, transactions for a single tenant are localized on a single worker node where the tenant exists. So you get like, the complex SQL coverage that, these relational apps have. Next, it also helps achieve the performance of single-digit milliseconds, right? So queries for a single tenant are routed to a single node instead of getting parallelized. And this helps optimize the network connection overhead and still scale compute and memory, because finally remember that all of these hundreds and thousands of tenants are present across multiple nodes in the cluster. Last but not the least, it helps you achieve scalability as the number of tenants grow. With the rebalance capabilities that Citus provides, you can add more nodes and shuffle, rebalance your tenants to these new nodes in an online way. You can Citus also gives you the ability to isolate large tenants to their own nodes and provide dedicated resources to get that kind of performance that is needed. The second type of applications are real-time operational analytic apps. These apps mostly have a customer or a user-facing interactive analytics dashboard. Hence, the requirement from a performance standpoint is sub-second for your queries. Typically, these apps have higher concurrency, at least 20 users querying looking at the dashboards at a given point in time. And the analytics is on fresh data, so it is real time. So based on my experience, I've seen that real timeness varies from 1 second to a few minutes. So the acceptable lag for data is 1 second to few minutes as a part of the ingestion pipelines. Mostly these use cases have a time series dimension present, and the tables are of the names like events, logs, etc. In these use cases, the common data model we have seen is it's a star schema data model in which there are few large fact tables and the rest are small dimension tables, and the number of tables are on the smaller side, tens of tables in the system. Once you've identified that your application falls in the real-time analytics bucket, you want to pick a distribution column that collocates large tables. So you want to pick a common column that is present on large tables. Typically, this column also represents the natural dimension to data or is the central piece of the application. So I have in a real world example where in the financial world, I have an application that analyzes securities trends over times. The security ID is a good distribution column because it also adds the natural dimension to data. In a user analytics workload where I want to get the usage metrics across my website, the user ID is a good distribution column because the entire use case is centered around this entity user ID. Column with higher cardinality and less queue. So you want to pick a column with higher cardinality and less queue, which we already covered. So here I have an example of user analytics and segmentation workload where I have bunch of tables. I have the events and user tables, which are the fact tables, and I have dimension tables, which are device types, event types, countries, etc. And if you see, I have the user ID that is present on both the large tables, the events and users, and that helps you collocate these large tables so the events can grow to billions of records or even more, and there are millions of users on my website. The rest of the smaller tables, the dimension tables, can be reference tables, so they can be replicated across nodes. Now, what are the reasons that you want to pick a column that collocates large tables in such real-time analytics workloads? The main reason is it lets you parallelize and push down SQL queries and avoid shuffling. As we already touched upon this concept of collocation. So once I collocate two large tables and by distributing them on the same column, Citus pushes the joins aggregates, roll-ups, filters, etc. down across the shards and maximizes performance. So here I have an example. If you see, when I'm running an aggregation query across users and events, and I'm joining them on the user ID, right? So if you see, Citus pushes the join down across the collocated shards, collocated data for both the tables, the users and events. It also pushes the aggregation down, if you see, count star. So at a high level, by collocating tables, you maximize the performance that you can get by pushing these queries down to the workers and executing them locally. The third breed of applications are high throughput transactional apps. And these apps are classic NoSQL document-like workloads, but they require the rich Postgres features like transactions, foreign keys, primary keys, triggers, extensions like Postgres. It's very common to see geospatial workloads and in an hour. Like there is a talk on geospatial, on building geospatial workloads at scale. So strongly recommend taking a look at that talk as well. And typically these workloads are based on a single key. So CRUDs are based on a key, and lookups, simple selects are based on that key. The throughput requirements are pretty high, starting from like, thousands to like hundreds of thousands transactions per second. The query latency is again in single digit milliseconds. So you want your APIs doing these lookups or CRUD operations to come back in like, single digit milliseconds. They have high concurrency. And an IoT app, which has again time series dimension, you have data that is coming in constantly, is a good like example of this workload. So the shard key in high throughput OLTP workloads is the column that is used for point lookups and that is present in CRUD. And again, this column adds natural dimension to data and is the central piece of application. In an example, right, like in an IoT workload, device ID is a good distribution column. And the reason is because you have these like short like point lookups that are routed to the right worker node, and you optimize network hop and still scale memory and compute, because finally in these IoT apps, your devices are spread across like multiple machines in the cluster. Here is an example. I have like events and devices table. Again, a pretty large table. The events is large and devices is like millions of devices. And the queries are like, get me the events for a single device, joining devices on the device ID and getting information for a single device, running a geospatial query, like where I want to see whether this device is in a specific, geometry, and queries like that, right? And one thing I also want to call out here is if you see that there is a JSON-B column, which is the detail, and this ties into me talking about, these use cases are like NoSQL, but they want like, the rich features that Postgres provides. So with JSON-B, you have the ability to store like, semi-structured and, unstructured data that these use cases require with Postgres. So to summarize, for multi-tenant apps, distribution column is the column that is at the top of the hierarchy, or the one that identifies the tenant. For real-time operational analytics apps, distribution column collocates the large tables. And for high throughput transactional apps, distribution column is the column that the application mostly filters on. To make it easy to pick optimal distribution column, we are exploring possibilities to automate this process given a Postgres workload. For example, for multi-tenant apps, to identify the tenant ID, we can leverage the foreign key graph, or if the foreign keys don't exist, generate relationships across tables based on joins and queries, and get the column that is at the top of the relationship graph. In real-time operational analytics, to figure out the column that collocates large tables, we can again leverage foreign keys and joins to identify relationships across large tables. And for high throughput transactional apps, we can leverage like, the where clause filters that are present in queries and identify the column that is mostly queried on. And for analyzing queries to get where and join clause, we can use tools like, the PG stat statements, which has the query catalog, or, the PG collector, which was mentioned in Andy Pavlov's talk, to capture queries for an existing Postgres workload. And the parsing of these queries to identify the where and join clause can be done via like, extension APIs related to like Planner and the query parser. The effort on this front, I would say, is very early, as use cases are pretty complex, and each use case has its own data modeling intricacies, which needs to be handled by the algorithm. So I'll leave it here. This could be a separate talk by itself. Just wanted to prime on what can be in store for the future. Thanks again for the opportunity for me to speak at Citus Con, and really looking forward for you to test Citus and build highly scalable apps with Postgres. Thank you.
All right, thank you, Sai. That was great. So a question from the audience. So what happens when one of the nodes fails? Will the data be reshuffled? Where do the copies of the data reside?
Yeah, that's a good question. So typically in a Citus cluster, the way you manage high availability is each of the nodes have a synchronous standby. So like the coordinator node, the worker nodes have synchronous standbys, and there is automatic call a failover that you need to configure. So if one of the node goes down, the automatic failover kicks in and the standby becomes the primary. All of this is managed in the is taken care of in the managed service offering on Azure, which is hyperscale Citus. If you're using like open source Citus, you could use like tools like Rep Manager or PG Auto Failover to configure that for you.
Got it. So we heard Andy talk about the self-driving database, and so what are the challenges for getting to a distributed self-driving database?
That's a great question, Marco. So as I already called out, like each use case has its own like data modeling intricacies, like in the sense that some use case, some workload has foreign keys, some don't have foreign keys, right? And coming up with an algorithm that like scales across like all these data modeling intricacies would be very important. And before that, like as Andy Pavlo mentioned, like how do we capture the workload and how do we like iterate through that workload to get information for the algorithm is again a separate challenge. So that's the reason I said that this is pretty early, but I'm very excited to see how this manifests. But yeah, hope that makes sense. Yeah.
Right. So what would you recommend to a user who's like has a complex transactional workload and they're already reaching the limits of a very large server? Like, well, can they use Citus? What would you recommend?
Absolutely. So the way I would do that is I would try to I would go through the workloads that I talked about and qualify which workload it falls, right? And identify that natural dimension to data, the distribution column. Once you figure that out, you can like build the application. So like that is the approach I would follow. But then there could be some like relational apps like that don't have the natural dimensions. It's a bit rare, but then most of the times you have this natural dimension present in data, like because you're finally building applications for users or like in the financial world for stocks, or like there is a natural entity that is present in your data. I would try to figure that out and then like distribute the data and like go forward, Marco. So yeah.
Got it. All right. And so just a personal question for me is like, what would make your life very much easier in Citus? Like what's the next big thing? What's missing?
Oh, I have many things, Marco. But I think the big thing is making this journey very easy for end users, like onboarding to Citus, like focusing on that aspect would be really helpful. I think that like the talk that I'm doing also entails the same topic, right? So basically the 3 steps that I covered, right? Like, qualifying use cases, like identifying distribution column and like, the data modeling considerations, which I did not like bring up. Some automation around it, like would be one thing which I really want personally, Marco. So yeah.
Got it. Makes sense. All right. Yeah, I'm also looking forward to that.